Current and potential difference in series and parallel circuits. Here I have a very simple model of a circuit involving a cell and a lamp. Charge, given the symbol Q, will travel round the circuit, carrying energy. It will collect energy from the cell and transfer it to the lamp. The lamp will then retransmit that energy as heat and light into the surroundings. The charge will come back to collect more energy, like this. Now current is the rate of flow of charge. So if we were to put an ammeter here, it would count the charges going past. If we put another ammeter here, it would count the same charges going past at the same rate, and therefore the ammeter here would give the same reading as an ammeter here. Voltmeters are placed in parallel with a component and measure the energy transferred to or from that component by every unit or coulomb of charge. A voltmeter across here would measure 1 unit of energy given to the lamp, and a voltmeter across here would measure 1 unit of energy taken from the cell to the charge. We now have two identical lamps in the circuit, and so the charges must give half their energy to the first lamp and half to the second. Again, the rate of flow of charge would be the same here, here, and here, so the current all the way around the circuit is the same. But a voltmeter across the cell here would measure 2 units of energy given to each unit of charge. A voltmeter across this lamp would measure 1 unit of energy given to the lamp, and a voltmeter across here would measure 1 unit of energy given to this lamp. So the value of the voltmeters across the two lamps would add to be the same as the value of the voltmeter across the cell. Here we have a simple parallel circuit with again two identical lamps. The charges come through the cell and pick up their energy, and now some of the charges go this way and through this lamp, while other charges go this way through the bottom lamp. They still come back empty to pick up more energy. If they go through the top lamp, they must give it all their energy before coming back for more. Likewise, if they go through the bottom lamp, they give up all their energy before coming back for more. An ammeter here would measure all the charges going past it. An ammeter here has only half as many charges passing it, and so would read half the current. An ammeter here would read half the current as well. If the lamps were different, we could end up with different values of current in these two branches, but we would still end up with a situation where the current through this branch plus the current through this branch is equal to the current through this branch. What about the voltmeters? Well, a voltmeter across the cell would show that 2 units of energy are being transferred to each unit of charge. A voltmeter across this lamp would show that 2 units of energy are being transferred to the lamp, and a voltmeter across this lamp would show that 2 units of energy are being transferred to this lamp, and so a voltmeter here, here, or here would give the same reading. So we've seen that the current entering a junction in a circuit must equal the current leaving the junction. The charges that come in must go out somewhere, they can't just disappear. We can show that with this simple diagram. This is the current entering a junction which is then splitting into this path and this path. If we know that 2 amps enter the junction and 1.5 amps are leaving through the top route, there must be 0.5 amps leaving through this bottom route. In all these circuits, we're assuming that ammeters have zero resistance and voltmeters have infinite resistance. This is not quite true in real circuits. In general, they come very close, and if in a question they expect an ammeter to have resistance or a voltmeter to not have infinite resistance, you will be told the values. Let's look at a more realistic circuit. Here we have a cell, a 2 ohm resistor in series with a 4 ohm resistor. We could place an ammeter here, which I'll call ammeter 1, an ammeter here, ammeter 2, and an ammeter here, ammeter 3. The ammeters go in series in the circuit. We could also have a voltmeter across the cell, voltmeter 1, a voltmeter here across the 2 ohm resistor, voltmeter 2, and a voltmeter here across the 4 ohm resistor, voltmeter 3. We've seen that the charges leaving this point will pass through ammeter 1, pass through the 2 ohm resistor, which I'll call resistor 1, pass through ammeter 2, pass through the 4 ohm resistor, resistor 2, pass through ammeter 3, and come back to collect more energy. All the charges that pass through ammeter 1 must pass through here, and here, and here, and here. So, current, the rate of flow of charge, must be the same all the way around a series circuit. I can therefore say that the reading on ammeter 1 will be the same as the reading on ammeter 2, and also the same as the reading on ammeter 3. The energy that the charge collects from the cell will be shared between the 2 ohm resistor and the 4 ohm resistor, and as the voltmeters record the energy transferred, the reading for voltmeter 1 will show the energy collected by the charge. That must be equal to the sum of the energy delivered to this resistor and to this resistor. So we can say that the potential difference or voltage is shared by the components in a series circuit. Or I can say that the reading on voltmeter 1 will be equal to the sum of the readings on voltmeter 2 and voltmeter 3. Giving some values, I'll say that voltmeter 1 has a reading of 3 volts, and in that case voltmeter 2 would have a reading of 1 volt, and voltmeter 3 would have a reading of 2 volts. The reason being, the 2 ohm resistor has only half the resistance of the 4 ohm resistor, and therefore only half the energy is needed to pass through it. The voltmeters read potential difference or energy transferred, so 1 volt is half the energy transferred as 2 volts. Using Ohm's law for the 2 ohm resistor, Ohm's law being current I is equal to potential difference V divided by resistance R. For the 2 ohm resistor we have a potential difference of 1 volt divided by the resistance of 2 ohms, giving a current of 0.5 amps. The current will therefore be half an amp all the way around the circuit. Let's look at a parallel circuit. Now I have a cell, a 2 ohm resistor and a 4 ohm resistor, again this time in parallel, and ammeter 1 measures the current at this point, ammeter 2 measuring the current entering the 2 ohm resistor, ammeter 3 measuring the current leaving the 4 ohm resistor, and ammeter 4 measuring the current coming back to the cell. The reason I've put these ammeters before and then after their resistors is simply because it makes no difference. we've just seen that the current entering the resistor will be equal to the current leaving the resistor. So it doesn't matter whether the ammeter goes here or here. I've got a voltmeter across the cell, voltmeter 1, across the 2 ohm resistor, and across the 4 ohm resistor. So as we saw with the animated circuit, the charge comes along here, having collected energy from the cell. If it goes through this resistor, it will transfer all its energy to this resistor, coming back for more energy. If it goes through the bottom branch, it will transfer all its energy to this resistor, before coming back for more energy. As the voltmeters measure the energy transferred, voltmeter 1 will measure the energy given to the charges, and this will be the same as the energy given to either this resistor or this resistor. So, voltmeter 1 will give the same reading as voltmeter 2 and as voltmeter 3. We can say that the potential difference of voltage is the same across each branch of a parallel circuit. The charges come along here and will all pass through ammeter 1, but then they will either go through this top branch, passing through ammeter 2, or they'll go through the bottom branch, passing through ammeter 3, before meeting up again to come through ammeter 4 and back to the cell. So all the charge will pass through ammeter 1 and ammeter 4, but only some will pass through ammeter 2, the rest passing through ammeter 3. So we can say that ammeter 1 will be equal to the reading on ammeter 2 plus ammeter 3, and that will be equal to the reading on ammeter 4. We can say that the current is shared between the branches of a parallel circuit. Now to put some figures in. If we say that voltmeter 1 is reading 3 volts, then voltmeter 2 and voltmeter 3 will also read 3 volts. Using Ohm's law again for the 2 ohm resistor here, we can say that I is equal to V over R, current is equal to potential difference divided by resistance. The potential difference now is 3 volts divided by 2 ohms, giving a current through the 2 ohm resistor of 1.5 amps. Using Ohm's law now for the 4 ohm resistor, again we have current is equal to potential difference divided by resistance. Potential difference again is 3 volts, but now a resistance of 4 ohms gives a current of just 0.75 amps. The 4 ohm resistor is twice as difficult to pass through as the 2 ohm resistor, so only half as much current is going this way as passes this way. As we can see here, 1.5 amps through the top resistor, the 2 ohm resistor, 0.75 amps, half as much, through the 4 ohm resistor, as it has twice the resistance. So we can say that the lower branch has twice the resistance, and so half as much current takes this route. In other circuits you may have different resistors, not just one being twice the value of the other, but it is possible to carry out the calculations. No, that's rubbish.